another minute and then we'll start.
I mean, it's
20
been,
years ago.
Somewhere.
yeah, that part's been done without, be done without a computer.
Zero stuff.
This was the equal volume case or the?
Yeah.
Equal volume.
Yeah. No, I don't think so.
And then there's, I think, two papers, one for equal volumes.
And it's the second one.
You're looking.
Okay, let's start.
Yeah.
So, pleasure to have Professor Neumaier from the University of Vienna talk about concise synthesis of types, grammars, and semantics.
Well, it's a pleasure for me to give the talk. It was a big stress because I lost my computer on Sunday and had to recreate everything from scratch for the talk on Monday and for today's talk. So it's less perfect than I would have liked to present it, but I hope you nevertheless will enjoy and we'll have an interesting hour and a lively discussion. So interrupt me if you need extra explanations or questions or comments. This is joint work with my group in Vienna, Peter Schrodl, Ferenc Domes, Kevin Kofler, Andreas Pichler, and David Langer. Peter Schrodl is no longer with us, but he's now working as a child care person. But the others are still active. So what we have been doing in Vienna was trying to create a system that automatically takes LaTeX and with minimal effort from the human side turns it into a fully formal semantic representation of the intentions of the writer of LaTeX, at least for the mathematical parts, not for cultural introductions and things like this. And this is work in progress. So part of it is realized, part of it is just proving of concepts, and part of it is still a dream. If this program is realized, which I think is less than 50 man years of work, probably less than 10 man years of work, then it would produce a huge repository of formal statements and proof sketches from all sorts of textbook and LaTeX documents, ready for formally proof checking. Because I am doing only the formal representation. So I turn LaTeX into a collection of claims, and I leave the proving of it, of the steps between them, to the theorem proving community, which is much better equipped to do that. Whereas I, as a mathematician, believe to be equipped to translate a mathematician's writing into something formal and doing in a fairly automatic way. So it would bridge one half of the huge gap between mathematics and theorem proving. Okay, central to everything are two pieces of software that we have. One is Concise, that's a semantic integrated development environment with a very flexible type system that merges types, grammars, and semantics into organic unity. And the second is Gen-Par, that's a dynamical puzzle for dynamical languages that change while reading a document. Please have a pen, but it's because of the stress in producing these slides. A dynamic language, that's one of the key features present in most of a mathematical document. We have seen on Monday that God started to write mathematics, creating a universe by saying, let there be light, and there was light. We say, let there be the real numbers, let there be a Hilbert space, and there is a Hilbert space. And the Hilbert space didn't exist anymore, it wasn't in the language, but after we have defined it, it is there. So the language of mathematics changes. And this is, I believe, the major innovation of my view that I'm presenting here compared to traditional views. In tradition, you have to produce first the whole language and you have to implement it, and then you can read something written in that language. That's borrowed intelligence in the sense of Monday. Today I will talk how to implement intrinsic intelligence, where you learn while reading, and that whatever you learn is properly represented so that you can use it afterwards within your language and you understand what it means. I have a project web page that's called fmathL.html. That's for formal mathematical language. And you can see there all the stuff we did until 2011. Then there was a break where, for lack of funding, we didn't have anything. And then in the last 18 months, we resumed work and did a lot of new things that is not yet well represented on the web for lack of time, but will be there soon. And it's, so all members of my research group spend most of their working time on other projects related to global optimization and optimization for industry. And this thing is our hobby. It's what we do alongside in our free time or in a little fraction of our paid time. We do it in such a way that there is no pressure. We publish little and we just progress until things are ready. And things are almost ready now, and some things are actually available on the web freely. So we have a small number of master and PhD students, 1, 2, 3, when it fluctuates. 2 professors, several postdocs that are supported by public grants on optimization, and the member of a startup company called DarkOpt, which is now 7 years old, specializes in providing advanced data analysis and optimization tools and interfaces for industry. It handles the entire process of problem solving, from the mathematical modeling to the development of a specialized custom software implementation. So we bridge in this particular domain everything from the mathematics to the computer science up to producing ready-made software that people from industry can use without knowing anything about mathematics. And part of the revenue of DarkOpt is invested into fmathL-related work, and that's for a few years we struggled to survive. Now we have a surplus, and that goes into new research of the type I'm going to talk about. Okay, so we have on the one side mathematics, we have on the other side formal theorem proving, and there's a big gulf between them. The very rough sea that takes a lot of effort to cross from one side to the other, and occasionally some brave people invest the work and bring a large harvest. So that's the current state. Now Mathland, that's where I live, that's why it is lively. It's informal, it's occasionally dangerous, that belongs to life. On the other hand, there's FTP land, everything is formal, therefore a little bit rigid, but it's fully certified. Here you can rely on things, here you have to trust things. Well, you have to trust also a little, but okay. So that's the current relation we have of math and formal theory proving. Now that's what's currently being built on the basis of mathematics, formal mathematics in the sense of Bourbaki, and formal theorem proving. There are a lot of solvers, I just picked 2 of the shortest ones. We are erecting in the middle a new pillar called Concise, which is supposed to give rise to a bridge connecting the two. And that's the vision for the near future, that across this bridge there will thrive from our side flexi-formal textbooks with formalized statements ready for theorem provers to try to prove them and to fill in the gaps, to correct mistakes and things like that. And on the other hand, I expect that some people from here will use the opportunity that there exists a nice bridge to create very math-friendly formal proofs, because that's something they can do with moderate effort. Okay, the drawings are from one of our group, who is not otherwise involved in the project, Santiago de Moret. So, we have seen on Monday that mathematics is a dynamic language. While you speak, while you write, while you read, you create context, you create language, you create value judgment. Now, value judgment is a difficult subject that belongs more to philosophy, so I don't say anything about it. Creating context, that's something that can be formalized, and I've been formalizing it through something called context logic, but I don't have time to talk about it today. I'll concentrate on the second thing, creating language. And I will do this by a small concept of proof, a LaTeX document of 5 pages called basic definitions, which we are going to formalize in the sense of formal specifications, not in the sense of formal proof. We are proving nothing. We are just setting up a system of concepts, the language belonging to it, and rigid, fully precise semantic interpretation. Now, mathematical language is highly optimized for efficient communication, and if you like, we can play afterwards a game. What does this mean? Where I play the concise computer as it should be in sometime in the future, and you give me pieces of text, and for each token you give me, I tell you what Concise would now know about the mathematics you are creating in this little piece. So this is a game we can play, and or we cannot play depending on the time. That's this. So most of all this highly optimized stuff for efficient communication is lost in current formalization, which results in a huge mess. Well, we have a low-level proof of gigabytes of stuff. But it's also a splendid opportunity, because if there are people who clean it up and make it intelligible, then it will be a lot of value. So, now from a formal point of view, at least from our formal point of view, each concept in mathematics, and actually mathematics in a very wide setting, in the sense of the art and science of precise concepts and their relations. So whenever you have precise concepts, you do mathematics. So computer science is part of mathematics in this sense. Large parts of theoretical physics are part of mathematics in this sense. So each concept is simultaneously a type, in the sense of type theory, well, almost, a grammatical category, in the sense of context-free languages, formal languages, and a record in the sense of C++ or Java class or so. And we formalize this in terms of type sheets, which is the basic thing that makes everything work. The abstract grammar of the language, that's that part of the grammar that is common to all languages, to all natural languages. I'm borrowing here a term from the grammatical framework, which is an existing framework for natural languages, which does all the declination and conjugation in 12 or 15 different languages, and which has very small components of specialized dictionary for target applications. Now, the mathematical dictionary is huge, and one of the things that we are doing is creating an interface to the grammatical framework. We have part of the interface, but it's not yet properly working. So all I am showing you will be mathematics without correct conjugation and declination, because that's just one step ahead. But it's not much ahead, it's maybe half a year or 1 year ahead. Okay, oops. The abstract grammar is more or less the same as the semantics if represented correctly, and I will show you why and how. It leads to type declarations. And then there are language-dependent concrete grammars, and they are part of annotations in a type sheet. And I'm going to explain you these things now. Okay, so that's a piece of LaTeX code. It's the beginning of a LaTeX file called basicdefinitions.txt. It has a few special markers that we need at present, at some later stage. We try to get rid of this as well. But that's some annotation that the user must provide. It's very little. He must annotate with raw pieces of text that are not formalizable because we lack understanding or we lack the context or whatever. So it's and then there are everything defined is, well, here it's called text VF, that's a little bit old. We have now here a define command. Every time a concept appears for the very first time, it must be marked. So that the compiler knows it's not a mistake, it's not an unknown word, but it's something that can be used from now on in the formal vocabulary. And essentially these two things are the only things that need to be marked. And there are a few very small things that occur very rarely that should be marked, but okay, this is the input to our Concise system, and the output is a semantic representation of whatever is in there. Now this is difficult to read, so let's look instead at the PDF. The PDF is this. That's how we define. At present, it's not a completely arbitrary mathematical text because that takes more time. This is a proof of concept. It's the way I define things. I've written a book. It's not published, but and it's in German, where I introduce for newcomers at university mathematics from scratch, assuming nothing. So I define what a set is, I define what a relation is, I define what logic is, I explain Greek letters, I define 0, 1 and everything until the end of the first year content of linear algebra and real analysis as taught at European universities. So everything is built up from scratch, and like my students should learn it from reading the textbook, so Concise should learn it from reading the textbook. And I show you how to start from nothing, just by simulating Concise. So, there are objects. Let there be light. And now there are objects. So you have a concept called objects. 0 and 1 are objects. At this point you don't know what objects are. You just know that it exists. But now you have at least 2 examples of objects. 2 is an object. Well, at some later point I have to explain that 2 is 1 plus 1, but because I need it at the very beginning, I just define 2 as an object, and it is an object with unknown properties. So, there are statements, there are real numbers. I have no idea what a real number is, but the system now knows there is something called real numbers, and it's a precise concept with properties that I will discover as I go on. A domain associates with every object X a statement X in D. So a domain is a kind of set, but it's not a set in the set theoretic sense. It's a set with structure, with arbitrary structure. The only thing characterizing a domain is that you can talk about containment. So, if an object is in a domain, we say that X is in D. This introduces a piece of grammar. From now on, is in means something, and you can translate the text into formal stuff. Because you can translate X is in D into this formula. Okay, the italic stuff, that's raw, that doesn't have to be interpreted by the compiler, it's just for us humans, it gives extra explanation. So in a domain, you have 3 notions, a notion of membership, a notion of containment, and the notion of cardinality. Now you as a human are expected to know what it means. Concise is not expected to know what it means. It's just expected to know how it is denoted and what's the words containing with it, so that it will be able to translate text into formulas. A type is a domain depending on the state of the semantic memory. Well, the state of the semantic memory is something not yet formally defined. So it's a phrase that appears in the type system that just says it's something that needs to be interpreted at some point. We write X in T if the object X has type T. There is probably some semantic thing missing because has is not yet a word that is well defined. So there are some slight bugs, and that's because we have not yet completed everything. Now, a category, that's not a category in the sense of mathematicians, that's a grammatical category, associates with every object the statement X in C. If X in C, we say X is a C. So X is a group. A group is a category. You cannot say X is in a group, because that's something different. And the mathematical language is very careful. From the way things are phrased, you can infer what the thing must be. Okay, then again some raw text that is not interpreted. Now a property P associated with every X, a statement X in P. In place of X in P, we also write P of X. If X in P, we say that X is P. So we have overloaded the in symbol by 3 different kinds of things which must be distinguished conceptually. Although in the end, instead of these, they would all be reduced to sets. But it's a mistake to reduce it to sets, because if you reduce it to sets, you implement it in a sampler and you lose all the meaning. It just keeps some bare logical reminder. That's enough to do formal proofs, but everything you lose helps a mathematician to make connections and to create meaning and proof and to find things. And if you lose this, a sledgehammer has to work hard to capture some of them and get it back. Whereas the mathematician has it easily, because he doesn't think in terms of ZFC, he thinks in terms of this stuff. Okay. Now I've got natural numbers. Now this is a little bit incomplete because it's just a proof of concept. We are introducing pieces of language here to create the grammar that a mathematician needs to understand things. So I'm skipping all the stuff. I'm skipping a lot of stuff and just pointing out things that are relevant for introducing additional additional ways of speaking. Because the ways of speaking, that's what a mathematician understands. That's what every student learns during the courses, and it picks it up and it gets exercises so that there's a unique agreement, and that must be formalized, and then a computer will be able to read the textbook like a human. So this is just additional, these are just many examples of additional piece of text that are that introduce new phrases. So now, a semiring, that's a domain such that for any A, B, and S, the domain S contains the sum A plus B and contains the product A star B. Sums are commutative and associative. Now we know as humans what it means. The computer must be told somewhere else, and I skipped that stuff. Products are left distributive and right distributive. A 0 of a semiring is an element 0 in S with A plus 0 is I, 0 star I is A star 0 is 0 for all A in S. The semiring of natural number is the free semiring generated by 1 and strictly ordered.
Well, you expect Concise to understand that left distributive and right distributive somehow refer to sum?
Yes, yes. That's everything grammatical is understood. Because there are phrases that tell, there is a grammar that tells how things relate to each other. That's part of natural language, and that can be formalized.
Yeah, well, it's not so obvious, because if you take the Booleans, for example,
Well, look,
product and distributive both over the OR and the XOR. So it's
well, I mean,
saying it's distributive is
the sum. In this context, this sum refers to this new concept introduced here.
No, what bothers me is left distributive referring to sum, whereas sum has just been introduced.
Sums are commutative and associative, that refers to sums, and products are left distributive and right distributive, and something distributive refers both to product and to sum.
Yes, but doesn't mention sums there.
Yes. But this is what a mathematician automatically generates, and that's what Concise automatically generates. There's a lot of context sensitivity in a human mind, and you need to represent all that formally in the rules how to go from text to formulas.
Okay. I'm just wondering how this works, or how this can work at all.
Well, there are two steps. What we do in what we have finished already is putting this into a formal internal representation that has all the semantics and from which you can reconstruct automatically exactly the same text. Then we have something called record transformations that brings the text-oriented form into a concept-oriented form. And this is in the process of building. We have done some things, but we have not done everything that I could show you, everything working. So it's, well, as I said, it's work in progress, but it's very interesting things that we are highly confident that we have soon something really nice to show. Okay, then we write this for the ordered semmering of finite cardinals with these properties. So that's how properties are introduced, just with and what. Then a strict order is defined by something. An order is defined by something. We write for the order and so on. Well, and this goes on. Now I define what a tuple is. A tuple is an array with a two-dimensional array with rows and columns and indexed by something. And then we can require an entry type for a tuple so that the entries have a fixed type. And we have a size, we have a column size, we have a row size, a transpose. We know whether a tuple is symmetric. We can do subtables, we can do column stacking and row stacking. That's all needed for if we want to teach the computer to automatically generate programs from analytic definitions of operations. So now you have cell arrays, count ranges, ranges. That's about how things are represented in the memory. You have a row-oriented table. You have dense row-oriented tables. And finally, you have matrices. A matrix is just a table whose entries belong to a semi-ring, so that you can do arithmetic on it. You can define the sum. You can define the product. And at this point, Concise should be able to create a program for matrix addition and multiplication that works. It cannot do it yet, but it has all the semantic information and it's properly represented. We just lack the record transformations to do it.
What would be the programming language?
Well, at first we would do it in MATLAB because it's very math-oriented. But it can, once you have it in one language, it's very easy to translate it in a different language because essentially you go through a parse tree and you just have to replace everything from one format into another format. So we have done this many times. We can represent things in Java or C++ or MATLAB or.
So now Concise is written in MATLAB.
Concise is written in Java. Okay, so then there are forms sparse dense matrices. The reason why we go this way is because that's what we need in our company to support our modeling work. So we of course develop first the stuff that pays back because DarkOp does not pay us for doing this work just for nothing. They want to have something back. And we are using Concise already for simple things. So Concise cannot do only mathematics. It can make things like we have a type sheet for project design in which you can design a project using precise concepts and relations. and it's mathematics in the sense I have mentioned, and it works with exactly the same thing. You can do everything that has a semantic, a precise semantics, and you can do it nicely, and as you'll see, it's not much work. You can write such a type sheet in one day, and then you can use it, and it will organize your everything nicely. Okay, so now type sheets, these are the central things these are pieces of text. Now the real thing is the internal stuff, which is represented in Concise, but to communicate it to humans, the humans write a type sheet. It's the semantic core, but it's an embodiment of the semantic core in a text. Each type sheet defines a semantically precise specification language and at the same time a very adaptive semantic type system. The type system was carefully crafted to mimic how I recognize types in mathematics. It's not undecidable. Any given record can be type checked in time linear in the size of a record, because what a human can do must be in time linear if it's done on a complex system. Otherwise, we can do very little once the complexity grows. So we cannot multiply 20 by 20 matrices because it's cubic, but we can read text that is endless because it's linear. Reading is a linear process. Okay, so in particular, because a type sheet defines a language, you can a type sheets serve as the representation of grammars in Concise, and they are passable by din-gen-par, by our dynamic parser. The type sheets themselves are also parsed using din-gen-par, using a grammar described in the type sheet, specifying the language for type sheets. So it's self-referential, and we check that actually this thing is closing and reproducing itself. So it's a semantically closed self-referential language. And this self-referential character is typical for the design of everything in Concise. We designed it because it ultimately should allow us to formally verify everything represented and done in Concise automatically, because the way Concise works is itself represented inside Concise. Okay, so to pass these 5 pages of trial text, we have a type sheet called concepts from latex.cnt. It contains 580 lines if you don't count annotations or comments. It contains 820 lines if you don't count annotations but comments. And it contains 1200 lines if you count annotations and comments. So these 1200 lines are sufficient to formally and automatically encode our proof of concept text, which are these 5 pages of PDF, representing everything a mathematician needs to know about it and to be able to work with the concepts. So it's usually we generate it in an interactive way, first doing things without annotation and comments, the basic things. Then we add comments, because after a short while things become undigestible for a human unless you add comments. And then we add annotations, which is grammar, and then we repeat this, and the type sheet grows to represent something real. Okay. So that's a type sheet. That's the beginning of the type, well actually that's the full type sheet without annotation and comments. It tells you concept that you have to import from other type sheets. There's a type sheet called text document, there's a type sheet called external type. And this is the only comment, so comments start with the exclamation mark. And now everything else is just type declarations. With a start symbol, that's the start symbol for the grammar. You can translate this automatically into a generalized Backus-Naur form so that you can send it to a context-free parser. In Par is more general than context-free because mathematics is not context-free, so you have to cope with more general constructs. So, now that's the first type declaration. The paragraph is this paragraph that was inherited from text document. And union means it's either this or this or this or this or this. So it can be anything that was it before, and now in addition it can be sentence link. Where sentence link is a grammatical concept that is defined somewhere below. The second thing is the sentence. It's also a union. It's either a comment or a statement or a definition or an assumption. And we know that it is. So every mathematician can write for everything they encounter, can write these things within seconds. It's completely automatic. The most complicated thing is to find good words that describe it in such a way that you remember exactly what it means and don't have to look it up all the time. But that is not difficult either. Then you have a comment. That's at the moment you have just one kind of comment. That's the raw thing that is already. We have statements that either specification statement or programming rule statement or dependent statements. There may be later other kinds of statements, tables and all sorts of things, but so this will have to grow. And I think we now have maybe 20% or 15% of what is needed to cover our textbook. And then, so, okay. At this point, we don't know what a specification statement is, but now we know it. It's something that must have a formula. All of means it must have everything that is listed here. And now let me give some a little implementation hint. How are things represented? Oops. I need both. Okay, so here we have something which is a specification statement. Then it must have a link, a field called var, and here must be something that is a formula. The semantic memory of Concise is a directed labeled graph which has nodes. Some of the nodes may be typed. It has directed arrows labeled by a concept. And here is something else, well, labeled by something. And here is another thing. And these specifications, the type declarations, tell what must be here. Well, what must be here. So suppose, so a formula, that's a union of several things. So actually, this doesn't have to be formula. It could be a Boolean formula, or it could be a set theoretic formula or so. But all these formula is a union of all this. So if you want to check whether what is represented here is actually a specification statement, you check whether this arg is there. It must be var. Then you check whether this thing is of the type formula, and it's Boolean formula, and formula is a union of Boolean formula, so you know that this is a formula. Well, it's not really a formula, it's only a formula if this thing is truly of type formula. How do you check that? Again, you go down one level, and it's not very difficult to see that this can be turned into an algorithm for checking the type in linear time. Okay. Now there are several kinds of types. We have so a programming rule statement must have a field called rules pointing to something which is an access protocol, and it might optionally have a connector, which is something you don't need for the programming, but you need for phrasing it, for talking about it, which is a word connect of type word connectors, and it has a feature link, which is of type feature link, and what these are is specified later. Okay, then you have a dependent statement, you have an informal statement, you have informal sentence 1. That's something interesting. It has a new kind of thing. We had unions, we had all of. Nothing means it's just an atomic thing without properties. So you don't need, you specify nothing. The next thing is a definition. There are many kinds of definitions, so it's a union of many things. Then define our objects must have all of. There are 3 kinds of things, so it must have 3 errors, one error to define, 1 error definer, and 1 error feature list, and that's what must be below. Okay, and it goes on like this. The optional things are things that may be present but don't have to be present. So it's the type checker checks if there is a link like that. If there is an error called feature link, it checks whether the object pointed to is itself a feature link. If it is not, you get a type error. If it is, but you don't need to type everything. You just click on a node and ask the system to type check it for you, and it will just type check everything that's below that and nothing else. This graph is not is a directed graph. It may have loops. In general, will have loops. So it's one has to do some marking to know when to stop. When one has covered everything below, everything reachable from that node. But this is not. This is a minor nuisance only. Okay, we have more thing. Here is a new kind of declarations. Sometimes you have one of. Well, either you have necessary feature or you have necessary feature formula. You don't have both. You have exactly one of them. And even in on off. Yeah, then you have just some words that don't mean anything. There's nothing. They're just needed for the grammar. And that's it. So that was the full type system that's needed for, it contains a complete semantic information about the meaning of these 5 pages PDF. Then comments, so for human readability, each of the actual type declaration is commented, and you can see how it is used by example, because this often tells much more than going through the formal stuff. And this is for easy human readability. And then there are annotations. So the annotations, they are the grammar.
So, sorry, this type sheet, was that written by hand or generated by the thing?
No, a type sheet must be written by hand because it contains domain-specific knowledge of the expert who builds the system. But it contains no mathematical knowledge. It contains cultural knowledge about how to do mathematics. That's a complete difference. All the mathematics is generated automatically from LaTeX. It's only the way we talk about mathematics and the way we form concept and the way we express concept that's in the type sheet. So it's the semantic structure, the abstract semantic structure is it. And now here, so there are different kinds of annotations. I'll give you just 5 examples. Actually, it's 7 because these are 2. Reading German text, reading English text, or reading Chinese text, or whatever. Everything you can represent in LaTeX, you can write grammars for. Writing German text, writing English text, creating text views in Concise for interactive processing, which is the elegant way of doing it. Automatic generation of human readable documentation, rendering algorithms, in particular programming languages, and things like that. And annotations, now look a little bit, they are not as comprehensible. You define the different kinds of annotations you want to use, and then for each thing you have, so you have here a union of these four things, and then you, for this is the LaTeX view, you have for a comment you say this, for a state, for a hash s, which is either this or this or this, you say this, and in this case it's the same for C and S, but for some reason, in a more complete setting, there you need to treat the two differently. That's why they have different abbreviations. Something raw is not internally represented, so it doesn't have a grammar associated with it. A specification statement reads we have something, writes we have something, but in German it writes with es gilt something. So it's and if you want to add a new language to your type sheet, you just add all these type declaration with a new target. So it's the translation work is proportional to the length of the type sheet. It's linear in the length of the type sheet, not in the length of the document you are translating, which is an important difference. Okay, now there are for optional things, you need to have some construct that may repeat itself and things like that. This is generalized backwards in all form, and you can do all that. Okay, I have 15 minutes left, yes?
No, actually, 10 minutes.
10 minutes?
Yeah.
But I started 5 past 10.
Yeah, we want to save some time for questions.
Okay, yes. So, okay, I explained already the representation. There is one more piece of representation. So, we can write one arrow like this, and we can write something as h.f.f dash and so on, which gives a very compact textual representation of pieces of the semantic memory. And one such thing that's called the SEM, that's the semantic union, semantic unit. Everything is just a collection of SEM in the semantic memory, including the internal representation of type sheets and everything. So that's how it looks on the screen if you work with Concise. You can unfold this or unfold these things. You can modify. You can do a lot of things. That's the a record view where you see the what you need to fill in. And unnamed nouns have some abstract number as name, and what is named by the user has its name. And you can see the type system which is used for typing this, and you can see what needs to be typed, and it's all done automatically. So that's a text view of a part of the thing I showed you, simple basic definitions. Okay, so I'll skip this. Okay, so I had said already most of this. There's something for programming in Concise. This is not very well developed, but we have a basic assembly-like language which modifies things on the levels of stems. We have record transformations, which takes one record typed in some format, in some type system, and translates it into something else typed in a different type system, which is essential for using, because if you you need the same thing set in different ways for different applications. Okay, so that's two different text views. One in which the formulas are in LaTeX, and one in which the formulas are partially parsed and are represented inside the semantic memory. So that's how you can work on, so this is piece of a type sheet, and that's how you edit a type sheet. So now let's say some words about the dynamic parser, because that's another new development. There existed no parser that can parser changing language, so we had to invent it our own. We had to take new principles for parser design. It's a mixed top-down and bottom-up approach, because using only top-down or using only bottom-up is very, very, very inefficient. And it's a parser targeted towards natural language, but we also used it for customized languages that we need for applications in DACOpt. It parses arbitrary parallel multiple context-free grammars, which is a generalization of context-free grammars used in the grammatical framework. It finds syntax tree for all possible parsers, so you can resolve ambiguity. Well, now you can represent ambiguity. Resolving it is something done interactively with human interaction, but later we will try to automatize much of it by using semantic context, because a mathematician can disambiguate anything. So computers should be able to do it also. Rules can be added at any moment during parsing. So if you pass a definition and some syntax defining some new operation that was never used before, you can define x and then and or something y, and let this be a binary operation. Or you can define a postfix operation or whatever, and it will be a new piece of syntax which will go into the system and which will be made known to the dynamical parser. It is a type-less incremental parsing of text. It allows next token constraints, because that's essential to parse things in natural language. It has either tokenized or scannerless parsing. We use tokenized parsing for parsing a whole text document, and we use scannerless parsing for parsing formulas, individual formulas inside the whole thing. It's written in C++, it's publicly available under the GNU General Public License version 2. It's fully integrated into Concise. Okay. So we have about a dozen applications of the parser. Two of them are related to automatic theorem proving. We can represent and parse the approach controlled language. We can represent and parse Humayun's MATNAT, which is not just a fragment, but which is supposed to be a complete controlled language for mathematical reasoning. It doesn't sound too mathematical, but it's usable. So it's some intermediate stage to what we want to get, and it has several applications. Yes, and the third one is the TPDP, but that's not yet in Concise. Before we did this in Concise, we made model tests in MATLAB, because in MATLAB it was most easy to represent the semantic memory. This is just a sparse matrix, and everything is very easy. Okay. To parse text documents, we are using LaTeX XML and Arc XML from Miller and Kohlhase, and we are using two beginners university textbooks, one written by myself and one written by my colleague, Professor Schiedl, on its introductory level mathematics. It's what we have in the first 6 weeks of for all the students. That's logic, set theory, elementary, so it's, and how to write things and how to prove things, and it's analysis and linear algebra. And our goal is to develop Concise far enough so that it can translate this automatically from German into English. Okay, there is something about disambiguation. Let's just give one example. At the moment, we can parse 3/4 of the two books. That's my book, that's Schichel's book. We can pass 3/4. 1/4 is ambiguous, half is unambiguous, and the other stuff is too specialized, so that we have not yet the grammar for it, but we will soon have it, and that's a good point to start. Thanks.
Questions?
So you say that you can pass 42% without ambiguities. Like when we do this for Mizar or Fleischbeck, basically every formula has so many ambiguities that we really have to do this statistically.
Yes, but it's so these are just the formulas that are in these two textbooks. They are written by one author each, so they are probably more homogeneous than in general. And also what we notice is that as we add more of the grammar to pass some of the remaining part, some of the other stuff starts becoming ambiguous. For example, the vertical bar means at first just the absolute value or the cardinality, but then it can mean divide, and once it means divide, you have many more possibilities, and some things that look very unambiguous to a mathematician, like this formula, suddenly has 3 different interpretations.
So that's probably because your language is fairly unambiguous currently. You don't have so much overloading.
Well, this is just this is not supposed to be the representative. This is just a momentary thing. I know much more about ambiguity and ambiguity resolution as a mathematician does it. So in the end, I expect that 95% of the formulas will be interpreted correctly in context, and only every 20th formula must be resolved interactively. And this 5%, that's something a mathematician is prepared to do, because it's just a little bit overhead over what they are doing anyway.
So you talked about having statements and definitions and so on. What about proofs? Do you have?
Well, we have proofs, but a proof is just an environment for making statements and for switching contexts. So a proof is a collection of statements and a collection of imperatives that we had in one of the talks last week, which tell what to do and what to change in some auxiliary memory that represents the proof.
So what proofs have you been able to parse?
Well, we have been able to parse all the Naproche proofs and all the Humayun-Madnat proofs. So everything they did, we can parse and we can represent. For Naproche, we had also an interface to TPDP, but only in the MATLAB version. It's not yet ported to Concise. For MATNAT, there was no binding to a theorem prover, and David Langer is a PhD student who just started and who has this as a project to do, to interface the MATNAT stuff to a theorem prover, so that the things represented in the proof can actually be checked there.
So at the very beginning of your talk, you have this picture with Concise in the middle of
Yes.
water, and you talked about the part of the journey between ideal world of mathematics to Concise. And I was wondering, do you have any idea of how to go from Concise to systems like whole or cup? So once we get this bunch of statements or concise text, then how would this help building the formal library? And I have a specific question in mind. So, for instance, from my experience, one thing which is difficult is when you have two texts summarizing, say, two different theorems, and they seem different in nature, but they both have in their dependencies the same theory. but they interpret this theory in a slightly different way. So if I take two texts and they both define what, I don't know, differential equation is or variances of whatever nature are, how can I make sure that definitions match, they have the same meaning, and, or would it become too different, too separated from the libraries in the end? This is the part where
Not that well, this is actually non-trivial thing, but it's something that a mathematician has always to cope with, because he reads a paper. The paper never states what the concepts mean. It assumes lots of concepts without thing, and you have to figure out as a mathematician what's the real meaning of it. The way this is done is like that. You pick the most likely meaning, the one that suggests itself naturally to you, and you have in your mind a question mark that might be, it means something else. For example, I have defined here a category, and the mathematician thinks of it, well, it's a category in the mathematical sense, but this is a category in the grammatical sense, so it's something completely different, it just has the same name. So the mathematician passing this would first associate it with category, because it's with category theory, and then it would immediately notice that if it tries to verify anything, nothing happens. That's proof that this is not that's not the meaning. So it's like Oban's system for checking which of the ambiguous meanings might make sense, because if it is supposed to make sense, it must be verifiable. So something must be verifiable. So you need some context, and that context tells you that this concept can be this, it can be this, it can be this. Now actually a mathematician has developed some skills in knowing that certain terms like a group always means exactly the same thing, while other terms like a floating point number means slightly different things to different people, because they have a different definition. Or nowadays it's better, because nowadays a floating point number always means a floating point number according to the IEEE standard. But 20 years ago, a floating point number was not something well defined. It depended on the implementation. So you will always have this, and you will have to make dictionaries translating between the different variants of the same theory. And this is the way to resolve it. Every mathematician has such dictionaries, small little dictionaries. It's just usually small things where maybe 10 or 15 items that translate between the notation of one paper and the terminology to that of another paper.
Yeah, am I correct that you've developed a parsing algorithm that's for ambiguous parsers that's linear time?
No, the parser
It's
is
the
cubic
typical ambiguous parsing algorithm.
The parser is well take cubic time. And in fact, it's the type checking is linear time. Parsing depends. Actually, the parsing is almost linear time. If you take a big document, it breaks a big LaTeX document. It breaks things down in linear time into its pieces, and then you have to work on the formulas. Working on the formulas is the hardest part. So it's usually you have the ambiguity only within a paragraph or within a sentence. And then these are short things, so it doesn't matter so much that the work is cubic there.
So it's cubic. You have a cubic parser. Yeah.
Yes.
So while you have the picture behind you, what about diagrams?
If you can formalize diagrams, if you can write them in LaTeX.
That's
Well, no.
that's just
If you,
avoiding the question.
There is a language, for example, for writing commutative diagrams from commutative algebra in LaTeX, or for writing Feynman diagrams in theoretical physics. These things are formal specifications of a diagram, and you can represent this. We don't have it, but a physicist or an algebraist who is interested, it's not difficult to write a type system for a fragment of things. He just
The pixel map of the diagram is also.
yeah, with
well,
pixel map you cannot argue. It's bad.
Well, actually, the deep learning people say that working with the picture presentation might be better than working with
Yes.
the text.
But mathematicians never do deep learning. The learning is very shallow, but very systematic.
I think
and it's much
mathematicians
more
also
efficient.
look at the picture rather than at the LaTeX when they want to like figure out what the diagram is.
Yes.
It's obvious in the picture that an arrow leads to a
But they look
certain
at
point.
but they look at the picture in a very formal way, so that it doesn't matter whether you write your diagram like this or whether you write your diagram like this. It's exactly the same. The mathematician argues about the abstract form of the picture and not the pixel representation.
Okay, let's thank Professor Neumaier.